So I've been looking through your self-assessments, and one thing I noticed this week is that several of you have been mentioning that things are starting to move a little bit fast. And another common thread that I noticed was folks saying that it sometimes was hard to get the big picture. Like, why were we learning all of these individual facts or these different matrix facts? Why does it matter that I minus H is idempotent, etc.? And so I thought it would be helpful today, instead of learning any new material, to just walk through what we've already learned and try to sort of tie a thread throughout the entire class so you can sort of get a big picture of how it all fits together. Because I think we're actually at a really good pausing point for that. And so for today's application exercise, what I want you to do is I want you to basically summarize what I'm going to put in these slides. So just go ahead and open a .rmd file and summarize what I have described, what I'm about to describe here, sort of summarize the big thread or the big picture of sort of what we've done so far in class in your own words. So this can just be a paragraph on kind of what the big picture is with all of these different rules and theorems and things that we've proven and learned, and kind of how they all tie together. So I'm going to try to summarize that for you now, and then I want you to summarize it back to me so that I can make sure that we're sort of all on the same page. And thank you to all of you that provided that feedback. It's so helpful for me to get these check-ins to make sure that we're all kind of on the same page. Okay, so what did we start with? So the first couple weeks, we really just talked about expected values, we talked about variance and covariance rules, and we talked about some general matrix rules. And this was basically the foundation that we built on the rest of the class. And so why did we do that? Well, because next we learned about least squares estimation. And we learned about this in matrix form, and so we needed some of these different pieces to be able to talk about this least squares estimation that we were doing, to be able to estimate basically the relationship between some predictors X and some outcome Y. And so in doing this, we talked about two things. We talked about law of total expectation and law of total variance. And that was because we wanted to be able to take the expected value of beta hat, and for that we needed that law of total expectation. And so we showed that the expected value of beta hat is equal to beta. And we did that using the rules that we had learned, as well as some of those matrix rules. And then we also wanted to know the variance of beta hat. So we wanted to calculate that variance covariance matrix. And that was sigma squared times x transpose x inverse. So we solved that this is the variance of beta hat using our variance covariance rules and also the law of total variance. Okay, so this was our first couple weeks. We covered expected values, variance, covariance rules, matrix rules. We built up to learning about least squares estimation. We added two more rules in here, law of total expectation and law of total variance, so that we could calculate the expected value and the variance covariance matrix for beta hat, our main estimator from least squares. Then we learned about what it means to be biased. And we showed that the expectation of beta hat minus beta is equal to 0. And so what that means is that beta hat is unbiased for beta. It's an unbiased estimator for beta. And we also talked about what it means to have minimum variance. And so what it would mean to have the smallest variance. And in doing so, we brought up again that variance that we had calculated for beta hat, sigma hat squared times x transpose x inverse. And why did we do that? Well, because the next week we were going to talk about what it means to be blue. So the blue is the best linear unbiased estimator. We know that least squares estimation provides the best linear unbiased estimator, and we wanted to prove what that meant. And so we showed that we basically found some beta tilde, some other linear unbiased estimator, and we showed that beta hat was better than it in all cases. And by better, we mean that the variance of beta hat is always going to be less than or equal to the variance of this beta tilde that we came up with. And so to do that, we needed to be able to use our information that we had learned about bias. And so we needed to show that this beta tilde that we came up with was unbiased, because we were comparing our beta hat from our least squares estimation to an unbiased linear estimator, beta tilde. So we needed to show that it was unbiased. And then we also needed to show what the variance of this beta tilde was. So we used some of those covariance rules, and we also showed that it was smaller, that our beta hat variance was smaller in all cases or equal to the variance of beta tilde. Okay, so then after that we learned about residual sum of squares, and we talked about what that was in particular. It was the sum of the residuals squared. And we used some matrix rules here to be able to determine basically some different pieces of this residual sum of squares. For example, we showed that the expected value of that was equal to sigma squared times n minus p plus 1. And we got that by using this trace/idempotent matrix rules. And so we were able to use some rules about idempotency, which we're going to talk about in just a second. And we also could use some rules about the trace to be able to get this n minus p plus 1 when we were calculating this expected value. And so again, when we took that expected value of that residual sum of squares, we used an expected value rule that we knew about, this y transpose times I minus h times y. And then we also used that idempotent rule to be able to do something with this I minus h, because I minus h, in fact, is idempotent. And why were we doing this? Well, eventually we wanted to get a good estimate for sigma hat squared. So we've been using this sigma hat squared in our different equations. We used it when we derived that variance for our beta hat, but we had never talked about how to actually estimate it. And so in order to estimate it, we needed to talk about what the residual sum of squares was. We needed to have a good estimate or expected value of that residual sum of squares. And we used that to be able to calculate an estimate for our sigma hat squared. And so we were able to show that our sigma hat squared was equal to the residual sum of squares divided by n minus p plus 1. And so to derive this, we needed the fact that I minus h is idempotent. We needed that nifty rule about how we could take expected values of when we were taking the expectation of matrices in a certain form, like that y transpose times I minus h times y. It took a certain form. That expected value always will take a certain form that involves the trace. And we talked about what the trace was and how we could estimate it for the hat matrix as well as for the identity matrix. And that's how we got this n minus p plus 1 piece. So that was important. So this is an important piece, especially when we're trying to calculate the variance and covariance, that variance-covariance matrix of beta hat. Because that variance of beta hat is equal to sigma hat squared times x transpose x inverse. We already knew how to do this part, but we needed to have a way to get this sigma hat squared if it wasn't given to us. Okay, so then we built on that by talking about f-tests. And a big part of the f-test is the residual sum of squares. We talked about how an f-test is a way to compare two models, a small model to a larger model. And we needed to have the residual sum of squares for this small and larger model, which is why we had to talk about how to estimate that via the expected value of that. And we also needed an estimate of sigma hat squared, because if we didn't actually have an estimate for the residual sum of squares, we know from our estimate that we learned on this previous slide that if we don't know the residual sum of squares, we can get to it by estimating the sigma hat squared times n minus p plus 1. So it's another way to get to it. So if we were just given the sigma hat squared, we could get back to that residual sum of squares. And that was important. For example, it came up on the content, the content assessment. And so these f-tests are important because they let us do hypothesis testing, which is what a lot of our statistical world consists of. And so we wanted to find a way to systematically compare a small model to a large model. And we wanted to create some hypothesis test that would let us see if these two are equal. So if the small model is just as good as the larger model. And so to do that, we built this hypothesis test framework that basically used an F distribution. We knew that this F statistic that we had calculated is distributed with this F distribution, and so we could use that to be able to find a good cutoff for our hypothesis test to determine whether or not we could either fail to reject our null hypothesis that these two models are the same, or reject our null hypothesis. And then finally, this all built up to confidence intervals, which is basically a way to quantify our uncertainty. And so our confidence intervals, they take that beta hat that we estimated from least squares using that expected value, the expected value rules, the law of total expectation, et cetera, take that beta hat and they multiply, or they add it and subtract it from t star, which comes from our t distribution, multiplied by the standard error of beta hat. And that standard error we pulled from our variance covariance matrix that we calculated using the rules that we've learned, and kind of building up to this kind of all along the way. And so hopefully this gives you a little bit of an overview of sort of where we've come from and why we did each of these pieces along the way to be able to get to this final step here. And so go ahead and open up an RMD file and just write a quick write up on kind of what you sort of perceive as where we've come from and how all these different pieces tie together. Just a quick paragraph will do, just to make sure we're all on the same page about that. That's our application exercise for today.